Hello everyone, my name is Noah McIntosh, and this is my assignment 7 for ENGR 459 Engineering Electromagnetics. And I'm going to be talking about the perfectly matched layer, or the PML, and its use in 2D finite difference time domain simulation, or FDTD. So we'll start off with an introduction to PML, and then we'll move into the theoretical concepts behind PML, its implementation into a 2D FDTD simulation. We'll go over a couple examples using a 2D FDTD PML based simulation, and then we'll finish off with a quick practical example and a brief summary. So to jump into the introduction here, we'll discuss why we use the PML, what it is, and its requirements. So here we have a simulation space for an FDTD simulation in 2D. As you can see, we have the X direction and Z direction, and a NX and NZ defined for both, so the number of simulation spaces in each direction. In all FDTD simulations, we're going to require some sort of a boundary condition around this space in order for it to function properly. So if we had a source implemented somewhere in here, whatever kind of experiment we have going on, when the waves hit this boundary, we need to be able to tell the simulation what to do. Ideally, we want to treat it as if they just go off to infinity in all directions. So that leads into the motivation for the PML. So the need is for a robust boundary condition for the FDTD simulation, and we want it to be able to handle any and all incident waves on the interface regardless of their polarization, incidence angle, and their frequency. We also want to eliminate the need to program and use various different boundary conditions. So maybe using an absorbing boundary condition and or a periodic boundary condition. So having one that's more robust can just allow the use of one. And the concept for PML, the perfectly matched layer, was originally developed in 1994. So what is the perfectly matched layer? So the PML is not technically a boundary condition. It is actually just a termination method. So it doesn't include any modifications directly to the finite difference equations at the boundaries. It is built into the update equations, as we'll discuss later. Essentially, it is just a lossy medium at the edge of the simulation space. So the PML region ideally will absorb all incident waves and allow the simulation to behave as if they go off to infinity. So in a perfect continuous world, the PML would always do this perfectly. However, when we introduce discretization, there are imperfections that can arise. So here we just have a figure showing the general implementation of a PML region in the simulation space. So the problem space in the center here is bound by the PML region. So this region is what the waves are incident on, and that is what we are governing and talking about here. So moving into some key concepts for the PML. We want to introduce loss in the region so that any waves that are absorbed are attenuated down to zero. But we also want to keep reflection to zero at the interface so we don't interfere with anything going on in the simulation space. So essentially, with the attenuation to zero, the PML introduces a Dirichlet boundary condition at the extreme edges, since it brings all the waves to the fixed value of 0 at the boundaries. PML can be used in 1, 2, and 3D. However, as mentioned, we'll be discussing 2D specifically here. And there are also different types of PMLs, like uniaxial or split wave, as we'll be introducing here. Essentially, they all still function as a lossy material on the boundaries of the simulation space, though. So before we get too far into the theory, we'll go over some relevant concepts and formula for the discussion. So first, the refractive index for a material is defined by the relative permittivity and permeabilities. The impedance, similarly, is defined by the permittivity and permeabilities, however, using a different relation here. And finally, we have Snell's law, which governs refraction between two mediums. So we have the refractive index included in both sides here, as well as the angles for incidence and transmission. So something to keep in mind as we go through the rest of the theory here. The problem statement for the PML is we need a boundary region that provides 100% transmission, so absorbing all waves, 0% reflection, and we want this to occur regardless of the polarization, incidence angle, and the frequency. So moving on to the theory here, we'll talk about the conditions for controlling the PML and how the PML relates to Maxwell's equations and the update equations. So we need to introduce loss in the PML region, and we need to manage reflection. So we introduce loss by bringing in conductivity. So we define conductivity within the PML regions, and we control the reflectance by adjusting the relative permittivity and permeability, and therefore the impedance and refractive index for the PML regions. It should be noted here that the conductivities that we bring in for the PML regions are purely fictitious. They only exist in the PML regions, and they're set to 0 everywhere else, so they don't affect any other parts of the simulation. So here we have the basic case of normal incidence, and it should be noted that the cases here are for transverse electric. So we have the incident wave, and we want 100% transmission, 0% reflection from this wave. So how do we get this? Looking at the reflection and transmission coefficients here, if we want the reflection to be 0, we need this top part to go to 0, and therefore we need the impedance to be matched. For transmission to go to 1, we also need these to be the same or matched. So now moving on to the oblique case, we again want 100% transmission, 0% reflection. However, now we have angles to consider. So moving on, we'll now have to consider Snell's law, and the reflection and transmission coefficients get a little bit more complex here. So we need the refractive index to be matched in order for the angles to be matched here, allowing the top to go to 0 for reflection coefficient and the transmission coefficient to go to 1. So this matching is where the name perfectly matched layer comes from. So summarizing here, the two conditions we need to meet for the PML region are we need to match the relative permittivity and permeability within the PML region, and it should be the same as the incident medium. and then we define our conductivities. So the relation here between the electric and the magnetic conductivity is derived from the curl equations, from Maxwell's equations, and that will be shown in a little bit. With both of these conditions met, in principle there shouldn't be any reflection from the PML region, no refraction, and the waves should attenuate to zero within. So how do we include this PML region into our simulation space now? We know the parameters that we have to implement and how to control this, but how do we actually put it into our FDTD simulation? The answer is we put them into Maxwell's equations. So we modify Maxwell's equations to include the PML conductivities. So on top, we have the basic curl equations that are used to derive the FDTD update equations. As we can see, conductivity is already present in the H curl equation based on the displacement current. So we can similarly introduce a magnetic conductivity. Once again, these are fictitious conductivities only existing in the PML region. And therefore, we add this into the E curl equation and we get two very similar formulations here. So the symmetry in these equations is where the relation between the conductivity comes from. Moving on, we need to break up our E update equation. So for transverse electric, we use EY, HX, and HZ. However, we now need to break up EY into EYX and EYZ in order to introduce the PML conductivities. So the equations here are expanded from the curl equations, and these are the four update equations used in the FDTD simulation. We have two for the Z propagation and two for the X, and as you can see, we have four separate conductivity values, each relating to a specific update equation. So we'll need to define all four of these conductivities in order to introduce the conductivity in the PML region. So here is just a further visualization of how they are defined separately. We have the conductivities in the X direction here, related as such, and then conductivities in the Z direction. So these are independent here. So now moving on, we'll talk about how we implement the PML in the actual FDTD simulation. So what values do we set in it? What are the requirements for the simulation? And then we'll discuss a modification of the PML region known as the Gradual PML. So the control parameters here are the conductivity, as we've been discussing, as well as the width of the PML region, and ensuring that the permittivity and permeabilities are matched within the region. So they can be changed as long as they are matched. A higher conductivity will introduce more attenuation, lower, less attenuation, and a larger width will give more room for attenuation, but will have less room in the simulation space. A smaller width will have less room for attenuation, but more simulation space. So typically the smaller width is required to be paired with a higher conductivity, and a lower conductivity with the larger width. So in practice, the PML conductivity and the width need to be selected basically through trial and error. So the exact values that are selected can be specific to a given simulation. The good thing about using FDTD is it's relatively easy to run a bunch of trials and hone in on values that are working, but these values may not work for all cases and may require adjustment depending on the experiment that's being run. So to quickly summarize here, we have the simulation space with the PML region and the various conductivities for each, so a magnetic and an electric in the X and Z, and the problem space bound by the PML regions. What's shown here is the standard PML, so a very sudden change from the conductivity within the simulation space, typically 0 unless there is a material defined, and the PML region, so a sudden jump here. In principle, this shouldn't be an issue, and the FDTD should function normally with the PML implemented this way. However, in practice, it can cause some erroneous results and some imperfections. So this leads to the use of the gradual PML. So this involves the slow introduction of the conductivity in the PML region, and it can help avoid issues such as reflection with very high conductivities. So there are a few different ways to implement the gradual PML. This method uses an exponential growth function. So defined by the equation here, we have the standard PML conductivity that's defined and would be for the whole region if we weren't using the gradual PML. And this value is augmented by this function here. So x represents the distance into the PML region, Lx the width of the PML region, and k represents the growth factor here. So this growth function goes from 0 to 1 across the width of the PML region, slowly introducing the PML conductivity up to the full value of c here. The larger the growth factor that is defined, the more gradual this process is and the higher the increase close to the actual boundary. So to give a couple examples, we have a plot here showing how this function progresses across the PML region. And the factor, as you can see, goes from 0 to 1. So for high growth factors, we can see 5 here. It is a very gradual increase, almost nothing initially, and then a steeper increase at the end. Whereas at low values, such as 0.5, it starts relatively high already, and then is a much more gradual increase up. At a k value of 0, the function simply goes to 1, and the gradual PML behaves the same as a standard PML. So using this gives you a little bit more flexibility. So we'll go over some examples here of the different PML regions that can be defined here. So this is the base case of the growth factor of 0, so standard PML here. You can see the conductivity changes very sharply going into the PML region defined in the yellow. Moving on, we have a growth factor of 1. So you can see here now we have a gradual increase of the conductivity up to the full value in yellow at the edges. Moving down, this effect becomes a little bit less pronounced, so the yellow region becomes a little bit thicker here. Moving forward, this trend increases, so it starts a little bit higher and is a slower increase to the full value. 0.5, this becomes even more pronounced, and then an extreme case of 0.1, you can see it is essentially at the full value, and there is very little increase over the PML region. Moving back to the case of 1.0 for the growth factor for comparison, we'll go the other way. So growth factor of 1.5, you You can see it is very similar into the region and grows much sharper at the end. To 2, once again, this becomes more pronounced. At 3, it is very similar a little bit into the PML region as it is in the simulation space. And then the extreme case of 8, the PML region is almost non-existent, and we have a very small layer at the edge where we have the full conductivity. So this allows us to have more adjustability over the PML region. However, there is another way that we can achieve more flexibility, and this is by defining each side of the PML region separately. So the coding here is a little bit more complex to introduce it into the simulator. However, the flexibility that is achieved is well worth it, as the width, growth factor, or conductivity of each region or each side of the PML can be defined individually. So again, we'll go over some quick examples here. This one shows some different widths for the PML boundary layer. Here we have different widths as well as different, or pardon me, just different growth factors. So 0 on the bottom, a very low one, pardon me, a very low one over here, and a very high one over here. Here we have different conductivities defined for each region. As you can see, the overlap here, this is a result of the order in which the sides are defined. So this one was defined last, meaning it overlapped what was previously defined in the corner regions. So care must be taken to ensure that you're achieving what you want when you implement the PML, and graphing it beforehand like this is a good visual representation. And then lastly, we have everything being adjusted. So different widths, different growth factors, and different conductivities. As you can see, very small increase in the PML region here, as here. However, these ones have high final conductivities, but much steeper growth factors. So now we're going to move into the MATLAB 2D FDTD that I've been using to prepare these graphs, and we'll go over some examples of the PML in use for simulation. So to set up our example here, we have a simulation space, 500 by 500 with 5,000 time steps. We have X direction here and Z direction here. And we're going to implement a conductive circular object in the center of the space with a conductivity of 50,000 and a relative permittivity of 5. And the radius is 75. So hopefully by implementing our source at Z equals 50, so about here, we're going to get a lot of reflections and some wild stuff happening to see how robust the PML really is. So we'll run 4 cases. First, with a middle-of-the-road conductivity and width value for both the standard PML and then comparing it to a gradual PML with a growth factor of 2. Then we will jump up the conductivity and dial back the width with the same 2 PMLs and compare the performance once again. All right, so now we are in MATLAB, looking at the 2D FDTD simulator. Quick review of the code here for the important parts. We have the source parameters, variable initialization, PML with the width and conductivities defined separately, as well as our growth factors, 0 for this first case with the standard. They are defined in the X and Z directions using for loops for each part. This section defines the permittivity and permeability if it is desired to be changed. Plot of the PML region, the object definition, then constants and coefficients for the update equations, the FDTD kernel with our update equations, source implementation, and our plotting. So we'll start off with this first case here. So we should expect to see good performance from the PML. With the standard, we should be able to see an outline of the region around the simulation space, and we shouldn't be getting any reflections from the region. So we can kind of see here where it's faded out, the outline of the PML region, and it looks like it's performing well. In the interest of time, I'm going to cut it off here, and we'll move to the next case, which will be using the gradual layer for the same simulation. We'll start it up. So here we should expect the same performance really. However, we'll likely see more of the waves as they reach the edge of the space here, as the gradual layer won't attenuate them as immediately as the sudden PML. Yeah, we can almost see them go right to the edge here, but we still are getting no reflections, so the boundary layer is performing well. Moving on, we will cut our widths here and jump up our conductivities, go back to the standard case here, and we'll see what we get. So with a higher conductivity, it's possible that we will start to get some reflections, in this case from the PML region. And it looks like that is what is occurring. You can see a bit of the reflected wave on the back here, as well as from the side. So that is not good performance. So we'll stop it and switch back to the gradual layer and see if we get any better performance. So with the gradual layer here, we aren't seeing any reflections actually, and that's due to the fact that the conductivity is ramped up. It's not immediately jumped up to that high value. So here would be a case where the gradual layer outperforms the standard. All right, so to jump back, we'll finish off with the practical example and then a quick conclusion. So the practical example for the PML here is a wave absorbing chamber. So we have an example here that's used for testing procedures. So anechoic foam is used to make these pyramid structures on the walls. And effectively, the combination of the material choice and the structures here absorb incident EM waves on the walls, and they don't cause any reflection. So the use here is for an antenna test chamber, Essentially, these walls and the foam structures are functioning as a perfectly matched layer for the testing. And then to summarize what we've talked about in the video today, the main advantages of PML are it's a very robust FDTD grid termination method, and it works with lots of incident waves, including various polarizations, incidence angles, and frequencies. However, there are some exceptions. It's highly adjustable, as we went over, allowing it to be tailored to given applications and experiments. And the PML is built into Maxwell's equations, so it doesn't require any special conditions for the finite difference approximation at the boundaries, and it makes it a lot easier in some cases to implement into the code. The PML is not a boundary condition. Once again, to reiterate, it is a lossy region at the edge of the simulation space. PML is typically considered the most state-of-the-art termination method. However, in some cases, absorbing boundary conditions can outperform it. The theory we discussed in this video was for 2D. However, the base theory for it is the same as for 3D. However, you're just adding another coordinate direction and therefore more sigmas in the PML region. And the parameters used to control the PML must be adjusted and fine-tuned to have the best performance. Here are some references for the information discussed here. Thank you very much for listening.